I'm going to talk about both versions of the fundamental theorem of calculus. Okay? Let me start by stating the version that you're probably most familiar with. One version of the fundamental theorem of calculus. Okay? Okay, so what this version of the fundamental theorem of calculus gives you is it gives you a technique to calculate certain definite integrals. Okay, if you're trying to find a definite integral with respect to a function that can be interpreted as the derivative of some other function, okay, then you can use that other function to calculate the definite integral. Okay, in other words, you can use the antiderivative of a function to calculate its definite integrals. Okay? Now let me show you the other version of the fundamental theorem of calculus. Another version of the fundamental theorem of calculus. Okay, and this is going to apply for a function I of x. Okay, so if we have a function defined as follows, then the following will be true. Okay, so let's take a moment to understand this other version of the fundamental theorem of calculus. So what I've done is I've defined a function in terms of a definite integral. Okay, and that's a perfectly legitimate function, even though it might look a little odd. Okay, we can even calculate values of that function, if that helps you to make sense of this. So for example, I of 4 would be the definite integral from a to 4 of f of t, okay? And I of a would be equal to the definite integral from a to a of f of t. We know that that's equal to 0 because definite integrals are equal to 0 when both limits of integration are equal, right? Okay, so if you've defined such a function, then the fundamental theorem of calculus says that for the two specified intervals, the function is continuous and differentiable, and furthermore, the derivative is equal to the function f. Okay? Now, this might look a little odd. Why don't we do some examples, and I'm fairly certain that that will help you to get a sense of this version of the fundamental theorem of calculus. Okay? Suppose you wanted to find the derivative of a function defined in terms of a definite integral. Like so. Okay? So the fundamental theorem of calculus tells you that you just have to evaluate the function t squared minus 3t for t equal to x. So that'll give you x squared minus 3x. All right? Hopefully that didn't seem so bad to you. Let's do another one. Suppose we wanted to calculate the derivative of a function defined in terms of the definite integral from 5 to x of e to the t squared. Okay, so that's equal to, according to the fundamental theorem of calculus, e to the x squared. Now notice that the bottom limit of integration did not affect the answer. The fact that I had a 5, it could have been a 50, it could have been 500, the answer would still have been the same. Also, you might not even know how to find the antiderivative of e to the t squared. Nevertheless, you can calculate, you were able to calculate this, you may have been able to calculate this, the value simply by using the fundamental theorem of calculus. Okay? Now let me have you do an example all on your own. So, can you calculate the derivative of the definite integral function that I just wrote? Okay, so pause the video and try to calculate that, please. Okay, I'll go ahead and do it. So that's equal to the tangent of x squared. Okay, so even though the second version of the fundamental theorem of calculus may look a little strange, using it is not too bad at all, or at least I hope you don't think so. Okay? Now let's do some other examples. Okay? So suppose we wanted to calculate this derivative. The derivative of the function specified the way I've just written it. Okay? Now, this does not exactly follow the pattern of the fundamental theorem of calculus. Okay? In math, that's often important. Okay? If something deviates from a necessary pattern, we can't assume that, with respect to a theorem, we can't assume that that theorem still applies. Okay? However, we can replace this expression with an equivalent form that does have the necessary pattern for the fundamental theorem of calculus. All right? You might know that if you switch the limits of integration, it introduces a minus sign. Okay? So let's do that. Okay, and you also might know that the derivative of a constant times a function is just the constant times the derivative of that function. So in other words, I can put the minus on the outside. Okay, and now we finally have a version that there's no doubt that we can use the fundamental theorem of calculus for. So that is minus f of x. Okay? So sometimes for similar problems, you have to find equivalent forms of the definite integrals to be able to solve them. Okay? Let me have well, actually, no. Let me work out another tricky example. All right. Suppose we wanted to calculate the derivative of the following definite integral function. Okay. Now, once again, this is not exactly following the pattern of the fundamental theorem of calculus. So we're going to have to replace it with an equivalent form. The easiest way to understand what I'm about to do is let's first define a function I equal to the following definite integral function. Okay? So the original expression is essentially asking for the derivative of I with respect to x squared, right? And we can solve that, we can simplify that, solve that by using the chain rule. So that's equal to I prime of x squared times the derivative of x squared. All right? Let's go back to the definition of the I function. So I prime of x, using the fundamental theorem of calculus, will give us f of x. Okay? And so going back to the equivalent version that we have there on the right side, I prime with respect to x squared is f of x squared, and x squared prime is 2x. So therefore, the original expression simplifies to 2x times f of x squared. Okay, let me have you try to do an example, a related example now. So would you please try to calculate the derivative of the integral from 1 to x squared of t squared minus 3t. Okay, I'll go ahead and do that now. So using the pattern that I just was discussing, you should get that this is equal to 2x times f of x squared, where f of x is equal to, well, here, f of x is equal to x squared minus 3x. So f of x squared is equal to x squared squared minus 3 times x squared. So 2x times f of x squared is equal to, simplifying, we get 2x to the 5 minus 6x cubed. Okay, and I hope that's the answer that you got. All right.